Good morning, good afternoon, everyone. Welcome to this webinar with Curtis Whitson. My name is Mohammed. I'm not Curtis. I'll be facilitating this webinar on behalf of Whitson. To start with, I'll just go through some meeting logistics so we're all on the same page. We're using Teams for this webinar. We have about 300 registered participants. So by default, everyone in the meeting will be muted. That doesn't mean that you cannot ask questions. Actually, we encourage you to ask a lot of questions, just that you need to use the Q&A chat box within the Teams app to be able to ask the questions, and I'll be moderating those questions for Curtis at the end of his talk. And that's where you see the chat box in Teams. The talk will be between 45 and 60 minutes with a Q&A at the end. We will be recording the sessions. We are actually recording right now. So you'll get a recording and potentially the slide deck after the webinar is done. And this is the webinar is facilitated by Whitson. We are a company that provides consultancy, training, and software services for the oil and gas industry. When it comes to the software, we have two main products: Whitson Plus, which is a web-based solution for unconventional petroleum engineering, everything from DCA to bottom pressure calculations, RTA, numerical modeling, nodal analysis. And we have also a PVT software, Whitson PVT, which is an EOS model development software where you can do the A to Z of PVT databasing and EOS model development. If you're interested in courses related to our software, you can go into our website, whitson.com/training. We always have updated courses there. We also have a list of public courses that you can join on demand, and also that are complimentary for anyone subscribing to our learning platform called Whitson Academy. And we also host webinars like this one throughout the year, generally about one per month, and you can find those also under whitson.com/training or in our LinkedIn page. And these are at least the two next scheduled webinars that we have. We also want to remind everyone about our annual conference that we hold in Houston every year. This upcoming year will be 2nd of October 2025. And if you would like to join, you can contact my colleague, Matthias Carlson. With that, I'll move on to our presenter. Very, very dear to my heart to do this presentation. Been working with Curtis for more than 10 years. He's the founder and CEO of the company, of Whitson. So the last name already tells. He's a professor at the Norwegian University of Science and Technology. He has been teaching, researching, and working with a lot of topics related to petroleum engineering, but then maybe the headlines would be PVT, gas EOR, gas condensates, and general petroleum engineering for both conventional and unconventional reservoirs. He has a bachelor's from Stanford and a PhD from the Norwegian University of Science and Technology. Of course, many of you have probably interacted with him, multiple decades of experience in the oil and gas industry, author of SPE Face Behavior Monograph and the Well Performance book with Mike Golan, and also has won multiple awards, including the SPE Anthony F. Lucas Gold Medal in 2011. When you ask Curtis about PVT, instead of saying, I work a lot with PVT, I think he would say that he teaches PVT, he applies PVT as a consultant, he has written PVT software, and his research revolves primarily, at least, around PVT. So with that, I'll give the floor to you, Curtis. You can go ahead and start sharing your screen and take it over from here.
Okay, thanks, Mo. See if I can get this done right. Let's see here. Okay, is it sharing?
Yes,
okay.
Sir. We're all good now.
And the audio is okay?
Audio is good, sir.
Yeah, and I guess my talking head is still there.
Yeah.
Great. So welcome everybody. The topic PVT, what's important and why. It's kind of a takeoff of a paper that we did maybe 30 years ago. A couple of colleagues, Evan Favong and Tao Young, and myself, we wrote a paper, gas condensate PVT. What's really important and why? And so this is a bit of a take off of that, but just more specifically around a generic PVT. I want to try to, I'm not going to talk about a bunch of equations and not going to talk about, any of the many details of what I've considered important and why I thought it was important, papers and cooperations and publications and things like that. The details which can't really be justified to go through in such a short session. But I think there's one common thing that I can say about this topic of PVT, what's important and why, is that I'm basically just an engineer, petroleum engineer by education. I grew up in the oil fields of Oklahoma, have been related to oil and gas from when I was a child, and pragmatically through applications of engineering saw that PVT was often important, and basically the goal is to try to figure out in any engineering endeavor that we're doing which particular PVT is important and why, and if not, then maybe spend your time working on other parts of the engineering task. That definition of whether it's important and why can change over time, and so I'm going to try to give this perspective of what do we mean by PVT, and then we're going to try to dissect this topic into what in particular, why it's important, and so forth. So let's get started. I want to, as I generally do the last few years, particularly since I started losing some of the people that have had greatest effect on my career, and in this, I've decided to call them PVT influencers. I guess in line with the youth term influencers on the internet. These people definitely had a strong influence on my understanding and path in working on PVT. Mel Standing, who was a teacher I had at Stanford, Keith Coates, who I met I think in 1992 and became a kind of a lifelong friend and mentor. Ken Starling, who was from the University of Oklahoma, didn't really meet him until I think it was in 1995. It might have been earlier, but I think it was 95. And then Michael Mickelson, who I met in 1985 and had the opportunity to discuss with these folks and to read and reread their publications and contributions to the topic of PVT. We have a kind of a talking about doing PVT, we have a kind of a work motto that we've got, burned into the entrance of our office here in Trondheim. And basically, this is a photographic image of that. It says, "Why speculate when you can calculate?" And this is something that Keith Coates would say to me on occasion when I would bring up some idea that I really didn't know the answer to and was just curious, what he thought about this or that, and then he would just always come back with this reflection of Curtis, why should we speculate when we can calculate and try to get to the bottom of the answers. And so I always had a lot of respect for that approach. When it comes to PVT, though, I think I want to modify this slightly, and I think that people like Mel Standing, who were heavily involved in influencing the measurement of PVT, would say, why speculate when you can measure and calculate both? And it also reflects on the calculations we do in PVT, where 90 hopefully 99% of those calculations we're doing within the realm of PVT have a foothold in measured data for the specific fluid system that we're looking at doing calculations for. We may be doing measurements of a small subset of pressure, temperature, and composition from the calculations where we're making fluid property estimations in a much wider range of pressure, temperature, composition. But we always try to tie those calculations and keep ourselves honest to make sure those calculations are honoring measured data in a certain limited range of pressure, temperature, and composition space. So I think this is probably a slight modification of that approach. When it comes to the term PVT, it's a bit misleading. It really stands for pressure, volume, and temperature. Now, in reality, we're looking at how volume changes with pressure and temperature, and composition should be in there as well for the systems that we're looking at, where composition can vary so much from place to place within the system and over time. When it comes to that, we need to know very clearly what it is we're interested in knowing the volume of as a function of pressure and time, pressure and temperature. So here on the right, I've got a simple descriptor of a single component, pressure versus volume, for a number of different temperatures in and around the critical temperature of a pure compound. And you can actually get some pretty complex changes in volume with pressure and temperature in and around the near critical region. You can have two phases, of course, vapor and liquid, when you're at temperatures below the critical temperature, and altogether you have some regions where the volume changes in a very, very simplistic way given by the ideal gas law. So we have call it very simple systems with some complex phase behavior. And then we have much more complex multi-component systems. So here on the left is an example of a CO2 injection test. I think it was Amoco maybe doing these tests back in the 70s when West Texas crews were being evaluated for doing CO2 miscible gas injection. So this has got volume on the y-axis and pressure on the x-axis. And basically looking at how that relationship looks as CO2 is added to a crude oil mixture, showing phase inversions where the oil phase becomes the lighter phase and the CO2 phase becomes the heavier phase, and a lot of strange phase behavior going on in that multi-component mixture. So the question is, what is it we want to look at in terms of the PVT description? So we're going to look at fluids for the most part. In petroleum engineering, we don't do a lot of work with fluids that are immobile. So we're generally talking about fluids that have some finite viscosity. But I'll go ahead and generalize and say that basically a fluid is just a mixture of one or more components. And what we need to know is the total mixture composition. And we use the term Zi to represent the mole fraction of the various components I found in the total mixture, which for most of the systems we're looking at in petroleum applications include the non-hydrocarbons shown here, nitrogen, CO2, and H2S, then a large number of hydrocarbons, methane, ethane, propane, through the hexanes, and then we get these heavier compounds, C7 plus, that go out and may be quantified out to as far as C30 plus, C36 plus, or even higher carbon numbers. Then in addition to the hydrocarbons, which is the main reason that we're, basically producing these systems, is to get the value out of the hydrocarbons. Byproducts and non-hydrocarbons are taken as they just vary from field to field. But then one thing we always have together with our hydrocarbon system is water, H2O. It's always there as a liquid phase, water aqueous phase in the reservoir, and the H2O partitions into the gas and oil being produced and makes its way to the surface and has to be dealt with in processing at surface conditions, as well as the effect it has on flow through the reservoir and in the production tubulars. In addition, I've got kind of a item here, ... talking about some components or compounds or species like salts or sodium chloride ions that are found in the water phase. This is a typical type of component. You may have injection of various non-reservoir components for dealing with production issues and problems in the production tubing and surface to various compounds that are injected, for example, at the bottom of the tubing and produce that together with the reservoir fluids. So we have a lot of different compounds to keep track of, and we basically have a quantification in terms of moles of component I. If you sum all of the moles for all of the components, we get a total number of moles in the system we're looking at engineering N, and then we just basically calculate this mole fraction as the moles in component I divided by the total moles in the mixture. So that's kind of and we need to know that molar composition in order to do calculations for sure. And so that's kind of where we're going to get started. By phase, the fluid phase behavior, by phase, we mean basically it's a homogeneous mixture of compounds. There are different types of phases that we usually label with the term vapor, liquid or liquids, and solids. What differentiates is vapor and liquids from solids is that solids basically have essentially an infinite viscosity, so it doesn't really flow per se, even though you have, I guess they say glass is kind of a liquid, like 100 years ago, a glass window that was made 100 years ago today would be measuring a thicker thickness at the bottom of the window than at the top of the window, because those silica molecules are moving very, very slowly over time. But basically, if you have a near infinite or infinite viscosity, we'll consider that as a solid. Now, when it comes to the differentiation between labels vapor and different liquids, I've shown an example here where we've got plot of pressure versus injection gas. Again, I think this is for a West Texas type crude oil. And I'm not sure if it's CO2 or an enriched hydrocarbon injection gas. Both types of injection gases can lead to the same type of complex phase behavior that we're looking at here, expected for somewhat lower temperatures, let's say in the range of 80 to 150 degrees Fahrenheit, where we actually see precipitation of solids. We can have multiple liquids, maybe the one liquid being a lighter liquid that's CO2 rich, and the other liquid being a hydrocarbon rich liquid. We may have only a liquid and vapor by itself. So you have a lot of different regions in this pressure composition space, showing many different numbers of phases and types of phases. So basically we're interested in each of these phases would be a homogeneous mixture of components that form from the original total composition of the system we're looking at. Normally we look at three phases: gas phase, oil phase, and water phase, or aqueous phase. That's typically what we're looking at in petroleum systems. In a more general sense, we can look at phase labeling as basically being labels that normally rank a a phase according to its mass density. So the lightest phase would either be a gas, or it could just be called the lightest phase. And we wouldn't really care. It wouldn't have any effect on its properties or calculations from at least a consistent equation of state. It would just be the lightest phase. And we might call that a gas if it has what we call gas-like properties. Maybe densities less than 300 kilograms per cubic meter or something like that. It's a bit arbitrary what we call it. And then basically we just kind of label the phases. We need some kind of labeling system that will normally label them from the lightest mass density to the heaviest mass density. And so for example, we just looked at the CO2 oil type mixture where we have a methane rich vapor phase. You could also have a CO2 rich vapor phase in that pressure composition space we just looked at. So the CO2 rich phase might be a vapor-like or a liquid-like phase. Then you might have a liquid that's hydrocarbon rich. But we also saw in that figure that the CO2 rich and the hydrocarbon rich phases that might have to change places if we rank them according to mass density. And then we've got typically the heaviest phase will be a water-rich phase, but in some cases we have oils that are denser, more dense on a mass basis than the water itself. The API is less than 10 degrees. So these are basically, these labels are not required to make calculations. They might be required just for labeling, for doing accounting. Then we've got the case of CO2 sequestration, which is becoming a larger and larger area of interest. So we typically, for an aquifer CO2 sequestration project, would have essentially two components, a CO2 and H2O. And then for most of the pressure temperature region, we would expect the CO2 H2O or the CO2 rich phase in the mixture, the CO2 rich phase to be the lighter phase than the H2O rich phase. But sometimes that flips. And even in this simple binary system, we can have the CO2 rich phase being heavier than the H2O rich phase at reservoir conditions. We've got solids. Examples of those in petroleum systems would be salt or scale precipitation from the aqueous phase, typically the wax formation of wax, which might be called a semi-solid because it might have some viscosity. Asphaltenes, which typically are kind of like rock. They at least look like rock. The asphaltene that I've seen pulled out of tubing and wells in West Texas after CO2 flood. Then we got hydrates, are a very special kind of solid. It's like really ice, where you've got these light components, methane, ethane, maybe CO2, kind of dissolve, so to speak, in the ice structures. And in some cases, the hydrate behaves so much like a solid that if you get enough hydrates in a pipeline, which can happen and has happened here in Norway, for example, then you basically can lose the entire pipeline because you don't have access to it, and it just basically forms a plug that may exist forever at the conditions it's in. So these are just examples of different phases, typically labels, and the labels that are ranked by mass density from light to heavy. And then when we're talking about the behavior we're looking at, the phase composition, or what we call phase composition or phase component mole fractions of each phase is very important. Without that phase composition, we can't predict properties of the phase. And without properties of the phase, like density and viscosity, compressibility, mainly density and viscosity, then we can't do engineering calculations. And so we need the phase compositions, and I use a generic label UI for that. Typically, we're talking about gas. We give it the symbol YI for a hydrocarbon gas and XI for the liquid phase in a gas vapor liquid system. So these are the mole fractions of the phases. And then we've got the ratio of the mole fraction of the light phase to the heavy phase, which we call equilibrium ratios or K values. And those component K values are I would say, the most important quantity in terms of understanding the partitioning of how the various components partition into these multitude of phases, from staying as a single phase to splitting into two phases or three or four, how many phases. How much of the methane goes into the lightest phase? How much of it goes into the very heaviest phase? And that component partitioning is a very important part of calculating PVT for each phase separately, because we need to know all the properties of each and all of the phases, because they will typically be moving and flowing through the reservoir, pipes, surface process facilities, and so forth. And the K values, though they're not rigorous thermodynamic properties like fugacity or Gibbs energy, Helmholtz energy, they are almost always used as a variable in solving the more rigorous thermodynamic equations of Gibbs energy minimization, for example. And you can get away without using the K value as a variable, but typically they are used to make those calculations more efficient. So the K values are very important to understand and to quantify. And there'll be different set of K values for each phase pair. So basically the light over the heavier phase in each of these cases, gas oil, gas water, oil water would all have their own set of K values, with typically all of the components or most of the components partitioning into both phases. Now, in some cases, you may have components that do not partition or are assumed not to partition into all of the phases. Example of that would be water. We make that assumption for 98% of the calculations we do in reservoir engineering, that water does not partition into the gas or the water phase. Typically, we don't assume partitioning when we do reservoir simulation, but as soon as those streams make it to the surface, you can be sure that the process engineers are putting that water back into the system so they can predict the amount of water being carried in solution in the gas and or oil phases that are produced, which is important to the surface processing. Here's a plot of the equilibrium K value for a gas-oil phase pair versus pressure. So we've got the K value versus pressure, and it's on a log-log scale, as you see here on the log-log plot. And we see a very characteristic behavior for each component. So if we take methane, for example, we can see methane has seems like a linear behavior up to about 500 to 1,000 psi. Linear behavior, which is the expected behavior based on fundamental thermodynamics. Likewise for ethane, propane, all of these hydrocarbons, likewise the non-hydrocarbons have the same behavior. So below about 500 psi, we've got this very simple relationship of K value versus pressure. And the intercept where that K value equals 1, for example, here for pentanes, I'm sure you can't read this, at 1, for the temperature of the system we're looking at, 120 Fahrenheit, for example, here, we can read off of this line here where it intercepts a K value of 1. That pressure is approximately the vapor pressure of that compound. So for pentanes, it would be down here around 35 psi. And then that vapor pressure is increasing for the lighter components, as you see here. Now, the K value at higher pressures, you see, has looks different. And what's different for these different curves is the total composition of the mixture being different. Some of these curves are for binaries, for example, methane pentane, normal pentane. Some are for mixtures of oil and gases. For example, the ones that go out and seem to converge out to, they basically have non-monotonic K-value behavior with a minimum in this K-value somewhere between around 500 and 1,000 psi. And then they approach K-values of 1 for methane coming monotonically downwards, and for the most of the other components being non-monotonically, they will converge to a value of 1 at some higher pressure, that we refer to as the so-called convergence pressure. And these K-values will look, the signature of the K-value plot will be the same for any petroleum reservoir in the world. They'll have the same characteristic low pressure behavior. They'll have the non-monotonic for the heavier components. They'll have the apparent convergence towards a convergence pressure where everything approaches 1 in K value. So this is going to be the same for every oil and gas system in anywhere. Now, we need the K values for what purpose? We need the K values so that we can make the calculation for our total mixture. We can find out what are the gas and oil compositions and how much of each phase exists. Is it 1 or 2 or 3 phases and so forth. Now, for each phase composition we calculate, we need the mass density and we need the phase viscosity. And why do we need these for engineering purposes? Well, the phase mass density is what's controlling flow in the vertical direction, be it in the reservoir, be it in pipe, vertical pipe, horizontal pipe. We have gravity segregation of the gas and the oil phase because of the density differences. So getting those density differences can be very important to many of the engineering calculations we make. What is the pressure drop, for example, in the reservoir? What's the pressure drop in pipe? So we need the mass density for basically any flow phenomena that involves the gravitational segregation. Viscosity obviously is kind of a friction, resistance to flow for any given phase, and that is given by the phase viscosity. So these are basically the properties that we need to describe the behavior of as a function of pressure, temperature, and composition. Now, we typically in petroleum engineering use the so-called black oil PVT model to describe the behavior. And basically what that means is that for the oil phase, we have 3 properties that are given as a function of pressure. The black oil table is created for a specific temperature. So all the properties here are only functions of pressure now. And we basically have the solution gas oil ratio, RS, the oil formation volume factor, BO, and the oil viscosity. Now, the formation volume factor and oil viscosity will be tabulated for 2 conditions. The one being saturated state, where the pressure of interest is equal to the bubble point of that oil, given by the solution GOR. And then also for pressures higher than the bubble point, where the oil is undersaturated. And the RS is constant, but we're at pressures above the bubble point. So basically, this describes the properties of the oil phase. Okay. And as we come back to the compositional description of fluids, we'll return and see how this solution GOR in reality is an expression for the oil phase composition. For the gas phase, for the equilibrium gas phase, this gas phase would be in equilibrium with the oil. The little rs, sometimes written capital RV, for example, in Eclipse 100, is the solution oil gas ratio. And that basically says that that gas phase can have so many stock tank barrels of condensate dissolved in that gas at a given pressure and temperature. And it'll keep those stock tank barrels in solution in the gas phase at reservoir conditions. So the little rs is really reflecting the composition of the gas phase itself, gas formation volume factor, giving the volumetric property of the gas at and above the dew point pressure. And then we've got the gas viscosity. Once again, the gas viscosity and the gas formation volume factor will be tabulated for both saturated conditions, where the pressure of interest is equal to the dew point of this gas, but also for pressures greater than that dew point for undersaturated conditions. And then finally, though not as often generalized for the water phase, often the water phase is assumed to consist only of water and no light components at all. You'll have the BO or the BW and the MUW describing the water phase in probably 95% of the reservoir simulations that are being done. And the assumption of how much gas is in solution, light components are in solution in the water phase is assumed to be close to zero. Now, in terms of treating this black oil model as a compositional model, this can and is being done in some petroleum applications. For example, the reservoir simulator written by Keith Coates, it basically will simulate black oil with a black oil PVT formulation or an equation state formulation. But what's done with the black oil is that you translate these black oil tables, traditional black oil tables, into K values and molar densities. And the components are a surface gas, which is kind of a collection of, let's say, the lighter hydrocarbons and the non-hydrocarbons, maybe C5 minus, C4 minus, and the non-hydrocarbons would be the surface gas, and the surface oil might be the C5 plus or the C6 plus. And then the surface water is often just assumed to be the same component as is in the reservoir water. So those are basically the three components. Typically, we only make calculations for the gas oil partitioning. We can calculate K values of the gas oil system from the RS and little rs versus pressure tables. So we can actually calculate K values for the gas oil system. And if we had, for example, a gas reservoir, a dry gas reservoir, and you wanted to take into account the water partitioning into the gas and the gas partitioning into the water, you could also do that using the RSW, little RSW, and the, well, in this case, for a dry gas, little RS would be zero here. Now, if you convert these black oil tables into K values, one component to surface gas, the other component to surface oil, you'll see that this on a log-log basis looks very similar to the K value of pure methane. And it'll be very close numerically to the K value of pure methane if you looked at this system in terms of a 40-component equation of state. The surface oil component K value has this characteristic non-monotonic K value behavior approaching 1, both of the components approaching 1 at some higher pressure here, convergence pressure. And this surface oil component reflects more or less the behavior, if you had a 40 component EOS, of how if you took C5 plus and just added all the components in C5 plus in the gas phase and divided by all the component mole fractions of C5 plus in the oil phase, calculated a C5 plus K value, then you would get a K value plot that looks numerically almost on top of this surface oil plot here, coming from the RS and little rs. So basically, the black oil formulation is a compositional formulation, but with only two components. Now, the BO will give us, together with the RS, will give us the mass phase density. The little rs and the BG will give us the gas phase mass density. And then the viscosity are just tabulated for saturated and undersaturated conditions here. So this is the equivalent, basically, of black oil. Now we can look at doing modeling with a full equation of state. We don't do this so often in reservoir engineering, but when it's done, it typically has this characteristic. We have total composition. This does not include the water component. So it's only talking about the non-hydrocarbons and the hydrocarbons, typically. We have an equation state model that describes the K values, so to speak, and phase densities. And then we have a separate compositional viscosity model. In this case, I've written LVC, which stands for Lorenz, Bray, and Clark. It's a compositional, so it's consistent at a critical point between the gas and oil phases being calculated by the equation of state. Some kind of a compositional viscosity correlation is needed to use together to get the phase viscosities in a consistent way. And that original LBC paper, I think, came in the 1960s, based on another paper by Jalsi and Steele and Thodas, I believe. It gave that original equation. The water treatment is typically, again, we do not assume any of the light components partition into the water phase. We assume that the water phase is consisting only of water component, and we have a single table of BW and MUW for getting the properties. Now, in this case, we have, as many as typically it's anywhere from 6 would be about as few components describing the non-hydrocarbon hydrocarbons, typically 10 components in your reservoir simulation, somewhere between 8 and 12 components where we lump together various component groups. Or occasionally in reservoir simulations, we may use as many as 15, 20, maybe as many as 40 if it's not a full field model, equation of state components here. And then we have a single H2O, which is treated again as a single H2O that partitions only into the aqueous phase. So this is typically how it's done for compositional reservoir simulation modeling. For surface process and to some extent pipe flow calculations, the water is included in the equation of state calculations and is taken into account in calculating typically 3-phase behavior, where all of the lighter components, really any of the components, can partition into the aqueous phase, and likewise the water component partitions into gas and or oil phases. That's important for the surface design and optimization of surface process facilities. Again, we've got the same concept of the equilibrium ratio that are used in the calculation of the phase compositions. And then from the compositions in the model that we're using, we're able to get the mass and molar densities and the phase viscosities. So bottom line, these are the types of numbers that we need to get for doing engineering calculations. For CCS, same thing. Typically, if it's an aquifer sequestration project, we'll only have 2 components, CO2 and H2O. We can, in fact, and very accurately use cubic equation of state, LBC type correlation for CO2 water systems. Typically, we can create K values that are tabular or equation form as a function of pressure and possibly temperature, together with the vapor and CO2-rich vapor phase and aqueous phases, but generated from an equation of state. You can also take into account the effect of sodium chloride, for example, on the solubilities of CO2 in water in the CO2-rich phase, using the same equation of state type approach. We have another webinar that talks about the method for doing that. At the end of the day, you basically end up with a 2-component system, unless you're doing CO2 sequestration in like a depleted hydrocarbon reservoir, in which case you would, of course, have all of the non-hydrocarbons and hydrocarbons that were present in that reservoir at the start of the CO2 sequestration project. And would need to take those into account. Again, the main phases being the CO2-rich and the H2O-rich phases, we need their mass densities and viscosities as a function of pressure and temperature. For some systems, they look at using CO2 is a working fluid for geothermal energy recovery, power plant generation, basically taking reservoir, injecting cold CO2, letting the reservoir heat it, bringing the warm CO2 to the surface, creating energy from that, and then re-injecting the cooler CO2. So in that case, you need to have the phase behavior, phase volumetric and viscosity behavior as a function of both pressure and temperature. So what is it we're trying to quantify in terms of PVT properties? We need the pressure and temperature of the total mixture. With that, we can calculate the number of phases. That's the first step in any of these software programs. You work towards finding what is the composition we want to look at in this particular part of our system, in the reservoir, in the tubing, in a given separator. We've got the composition, we've got an estimate, or we know the pressure and temperature. And the first calculation you need to make, regardless of using Blackwell properties, the equation of state model, is how many phases will that mixture split into? Will it remain as a single phase, or it will split into two or more phases? So that's the first thing. Once we know the number of phases, we need to know the amount of each of these phases. And we do that in what's called the Rashford-Rice, or the phase split calculation with knowing K values and ZI. You can calculate the relative molar amounts of each phase in the system, in the total mixture. Now you've got the total amount of each phase. At the same time you're solving for that molar amount of the phases, you actually get the calculation on the cheap and free of the component mole fractions for each phase. So those are determined in the process of solving for these molar amounts. And that's an algorithm called the Rashford-Rice calculation. Now, what you then do is you take these component mole fractions of each phase and you check with your equation of state, are those two phases, gas and oil, in thermodynamic equilibrium? So we have to calculate fugicities or Gibbs energy of each component in each of the two phases, and make sure that methane has the same energy in the vapor phase and the liquid phase. Likewise for ethane, a different energy, but needs to be the same in both phases. And if it's not, then we have to go back and redo the calculation again with a different set of K values. And you keep iterating on those K values until you find a set that gives you the number of phases, the phase amounts, phase compositions. And when you check those phase compositions, the EOS model says, yes, chemical energy of methane is the same in both phases. Chemical energy of ethane is the same in both phases, and the same for all of the components in the mixture. At that point, you've converged the so-called flash calculation or equilibrium calculation. Once we know the compositions that are in equilibrium, we can calculate the molar mass or molecular weight of each phase. From the molar density given by the equation of state, we get the mass density, of course, which is needed for doing engineering that involves gravitational segregation of the phases. And then we get the viscosity from the viscosity model, knowing its composition, pressure, and temperature. Now, if we look at most of the calculations we're doing, particularly in pipe flow and reservoir flow, we basically have volume elements. Okay, and we have to solve this flash calculation in all of the different volume elements. In a reservoir simulator, we might have anywhere from tens of thousands of grid cells, volume elements in the reservoir describing the geological structure containing the reservoir fluid system, to tens of millions of these grid cells. And in each cell, at each time step, which might be the length of a day or a month, you have to solve this flash calculation, knowing an estimate of what's in each cell. You know that because in the previous time step, you know exactly what the molar composition was in the cell. During the time step, you know what's coming in from neighboring cells, what's going out into neighboring cells. So you get this material balance within the cell, and you've got an estimate of the pressure, maybe the pressure and temperature. So you have to go and do this calculation for every cell at every time step. And basically what you have to do is that it's an iterative process, because like in a reservoir simulator, you don't really know the pressure in each grid cell, but you have to choose it so that with the known number of moles of each component, total number of moles, you know the grid cell volume at each time step because you know the original pore volume for that cell. You know how that changes with compressibility of the rock. And so you know that you have to fill that cell volume with the number of moles. And if the number of moles you've assumed with the pressure you've assumed doesn't satisfy the constraints of the basically the molar and volume constraints, then you have to iterate on the pressure for all 10 million cells until you converge all of these constraints. That's basically reservoir simulation in a nutshell. And similar type calculations is done in pipe flow. It's just you've got fewer number of these volume elements. Now, where do we come up with these PVT properties? So in the 1930s to about the 1960s, there was a lot of experimental data coming out of laboratories. For example, university laboratories, University of Michigan, Cal State, the Department of Energy, and it wasn't called Department of Energy back then. But basically you had organizations and then public organizations. Then you also had companies like Chevron. When Standing left University of Michigan, went to Chevron, Standard Oil, they created PVT laboratories and did their own measurements there. We had commercial laboratories like core laboratories and others that have developed. And basically we got some of those PVT data being measured were published in the literature. Some of those were made specific to fluids in a given reservoir, and that started becoming very common in the 50s when you had commercial laboratories available, company laboratories available. And then we started doing computations to come up with these PVT properties with models. And the first models that were developed were basically empirical correlations based on graphical correlations that have been developed in the 1940s. Many of them 30s and 40s and 50s. So they did graphical correlation, like this Standing Cat's Z-factor chart for gas was a graphical correlation before it was converted into an equation later. And so these empirical correlations were made in this period of time, 1940s to 1960s. By the late 1940s, around 1949, we started getting equation of state. The Redlich-Kwong came in 1949. You had the VWR, Benedict Webb-Rubin equation of state. And then by the 1970s, we have the two equations of state that we use today. The Peng-Robinson came after the Suave Redlich-Kwong, which was a modification of the original Redlich-Kwong. I think SRK came in 72 and the Peng-Robinson in 77. And those are still the two main equations of state being used. These are cubic equations of state being used today. And then compositional viscosity correlations started showing up in the 1960s. Like I mentioned, the Jausi-Steele-Thodos method that was adapted by Lorenz-Behr and Clark. And then some corresponding state methods, Pedersen, late 90s, early 2000s, I think. But what's common now is that we basically create fluid-specific, or I would say field-specific, reservoir-specific EUS, LBC models that are developed based on fluid-specific laboratory PVT data that are often measured either by the company's laboratory or commercial laboratory or a mix of the two. So we basically built these EUS, LBC, or EUS viscosity models that describe at minimum one sample, and the PVT data measured on that one sample, to literally hundreds of samples for a given reservoir or a given field to develop a single equation of state model. So what do we mean by important? Basically, it's any PVT property that will have an impact on costs, major revenues, will have an environmental impact, health and safety impact. So just as an example, for revenues, gas and or water EOR, the density of the injectant and the oil, viscosity of the injectant and the oil, the interfacial tension, the component partitioning of the components in the gas and oil phases become very important to the success of the EOR project, bringing it from, let's say, lower 10 to 20% depletion recovery to 40 to 60% recovery with EOR. The surface processing can bring a lot of added value by extracting as many of the components into the liquid phase, the so-called oil products, instead of gas products. And that's controlled by basically the K values at lower pressures and temperatures. Environmental impact, we've got methane loss, for example, storage tanks or transportation tankers, both from oil and water tanks. Basically, methane loss, VOC losses is an important environmental issue. Health and safety, obviously H2S is a dangerous compound in connection with field operations and drilling. When it comes to costs, there are many issues and important costs. I'll just running a bit out of time, but basically, how many platforms are needed in offshore fields? It has to do with recovery mechanism, well spacing, the diffusivity term, K over mu. Obviously, the viscosity is important, compressibility, density, gravity segregation, viscosity for flow and porous media. The number of wells required, again, same properties, essentially controlling the recovery mechanisms. Again, pipe dimensions for pipe flow, both of injected fluids and reservoir producing fluids and mixtures of the two. And then we've got compressors and pumps, a little out of my realm, but basically density and viscosity, as well as some thermal properties as well. Now, some of the gravity friction losses will lead to additional cost because of added pressure losses. And in some cases, gravity and friction will give a positive effect on revenues for particularly displacement efficiency in reservoir conditions. Surface processing, we've already mentioned, for the K values and controlling the K values through different surface processing units, dew point controllers, for example, bringing more value to produced well streams. Basically, we've got different groups of engineers going to look at different parts of the PVT. We've got basically reservoir to the wellbore. These are the reservoir engineers. Wellbore to wellhead, we got the production engineers, artificial lift, compressors and pumps. Processing engineers, we got the process units, compression, flow assurance engineers, getting the fluids to processing and market, and then finally process and final refining, chemical engineers. So basically everybody has their own range of pressure, temperature, composition, varies over time, and each engineer is wanting to identify as early as possible what PVT properties are important, why they're important, and do their importance change over time. So in my opinion, the obvious reason why we're concerned about this is because it does have an effect on bottom line numbers, and we have to figure out how and when PVT are important. It's not intuitive to most of us, and it requires a systematic analysis throughout the system. So just in summary, that's what I wanted to kind of go through. Keeping it in perspective, sometimes very few PVT issues have any impact on anything. Sometimes PVT drives the development of a reservoir, for example. And so with that, I think we're running out of time. I'll try to field any questions, Mo. if there's any
Yes,
time for
sir.
that.
A couple of questions here. So to start with a question from Juan, for unconventional reservoirs with large number of wells and different GOR, what's the best strategy to manage and utilize PVT data effectively without becoming overwhelmed?
For unconventional reservoirs, can you repeat the question? I was just trying to get my.
Yeah, I think mainly related that you have a large number of wells and also a large variation in GOR. So what's the best strategy to both manage the data and utilize it in an effective way without becoming overwhelmed by the large number of wells and the large number of potential samples that you'd have to collect or PVT reports?
Right. Yeah, so it's a major problem because we have so many wells. These wells in the tight unconventionals typically have fluid producing GOR ranges that go from low GOR to increasing GORs up towards near critical oils. They go flip into near critical gas condensates, leaner condensates, all the way down to dry gas. So some of these basins have all types of fluid systems. So using empirical correlations is just not a generally a good approach. Very difficult to get any of these generalized correlations to describe anywhere near critical phenomena, right? So you need an equation of state. So what we've tried to do in most of the tight unconventional basins is to, together with a group of companies, collect if not 100 or more samples from different regions within the basin itself, try to develop an EOS viscosity model that describes all of that range of samples, a single equation of state model. So that's the first step. And then the second step, when successful, not if successful, was when successful, it can be done, it's just difficult. But when successful, you then have to be able to take daily production GOR or well by well production GOR to estimate the local drainage producing well stream composition that you believe describes what's flowing in the reservoir to create your, for example, black well tables, to do most of your engineering analysis with a black well table. So that's the approach that we recommend using. The equation of state is used to create the Blackwell tables together with a known assumption or knowledge of the producing GOR for a given well. And it needs to be in some way automated because there's so many wells. So it's very different than conventional type of PVT treatment.
Very good. Thanks, Curtis. And then there's a question from Jan Min about CO2 being supercritical at reservoir conditions or above the critical point of CO2. What would you call that? Is it considered vapor or liquid in a phase diagram?
Yeah, so we're talking about pure CO2. Was that the question, or a CO2?
I assume that's the case. Yeah.
Yeah, and CO2. So, to me, the term supercritical is, I guess, a pressure and temperature that is higher than the fluid, the system, the ZI critical point. Okay, so higher temperature and higher pressure than the critical point. And a second part of that would be that it's in the single phase region. So in that quadrant, in that northeast quadrant of the pressure temperature diagram that we're kind of starting the supercritical definition about, it may not be single phase everywhere there. Okay. And if part of that quadrant is two phase, then you have to leave that out, in my opinion, of talking about supercritical behavior. So it's single phase, it's in this northeast quadrant. And to me, it's like unnecessary to have a label for that condition. Every mixture we talk about, be it in what's flowing into a separator, what's flowing into a reservoir, you add CO2 to to a water system, to an aquifer. Every grid cell, every part of the reservoir will have a different total composition, CO2, water. Every mixture will have a different critical point. Okay? And so to me, it's a label that doesn't help us handle quantitative PVT analysis. It's just a label. The point is that all these equations of state models that you can use and should use to describe the CO2 pure or the CO2 water system, or even a CO2 water system with impurities like methane and ethane. The equation of state will first thing do tell you my mixture at this pressure and temperature is 1-phase, 2-phase, 3-phase. And it'll tell you the amount of each phase. It'll tell you the composition of each phase. And for accounting, we may want to label the different phases: gas, oil, water, or whatever. You may want to give them labels, but you need to have a reason to give labels. Okay? And so to me, the supercritical label is basically limited to a single phase condition that happens to be higher than the critical pressure and higher than the critical temperature of the mixture. And that critical point will move all around in a sequestration project. And if you're only looking at CO2 itself, then it's, to me, not so interesting because it's just single phase. There's nothing really special going on there. That is how I see it.
Yep.
My philosophy in general of life is the fewer labels we have, the better off we are.
Makes a lot of sense. We have a lot of questions, but I think just for the sake of time, we need to just wrap it up with one final questions. If you have some concrete examples where wrong PVT handling had a significant impact on outcomes of a project.
Well, in terms of dollars and cents, we don't get involved in the economics of these big projects. We're providing support to get accurate PVT to minimize the uncertainty and risk of PVT effects on major decisions. So the fact that we've been used, we and others are used on a regular basis to provide accurate PVT, reservoir, production system, topside, for sure, almost every project I would think in the petroleum domain has had major impact of PVT on different parts of a field development. I think the examples would be, I think it would be hard to find an example field development where PVT wasn't important to have right. Yeah.
I think one example that I just remembered now, Curtis, is like the Macondo blowout, for example. Their PVT could become an important thing to determine. Also, I think it was the penalty to be paid, right?
That's right. So it's this is that was a very, very special and peculiar situation where PVT was important for basically the fines being levied on the blowout itself. But yeah, I think it's it's the rule. But if you're doing water flood, low GOR oil, if you get the viscosity and density right of the oil and the water, you're 98% of the way there, probably on PVT. And you can do that by yourself probably without our help. So
perfect. Thank you so much, Curtis, and thank you everyone for attending. We'll send the recording of the webinar.
Thanks. Yeah,
Thanks.
take care.
Bye now.
Bye-bye.